There are two more partial differential equations from physics that I would like to discuss, both of which are formulated in the language of vector calculus. We are nowhere close to actually discussing them in any detail. That is something you will also do in more specialized classes later on. But I think it's very helpful and perhaps motivating to have a look at both of these partial differential equations. The first one is the Navier-Stokes equation. Again, one particular variation of the Navier-Stokes equation, which is very important in fluid dynamics. The Navier-Stokes equations involve a vector field u, which describes the flow of a fluid. This vector field u describes how the fluid flows in space. And that vector field satisfies the following partial differential equation. The time derivative of u plus u, scalar product, the gradient of u, whatever that is, equals the negative gradient of P. P in this case is the pressure, plus alpha times the Laplacian of u. You need to be careful here. Plus the force vector field F. U is the flow vector field, which describes the flow of a fluid. P is the pressure variable. And F is an external force vector field. That could be, for example, just gravitation. And in addition to that, we know that the divergence of u equals 0. There are a few caveats here, and those are the reasons we cannot discuss Navier-Stokes equations in too much detail at all. Please notice, here I'm talking about the gradient of u, and okay, we have actually not discussed the gradient of a vector field. We've only discussed the gradient of scalar fields. So this is a bit outside of the scope of what we have done so far. And similarly, here I'm taking the Laplacian of a vector field, which is also outside of the scope of what we have done so far. In both cases, we just apply the differential operators component-wise. For example, the gradient of a vector field would just be take all the gradients of each component, which in that case would actually be a matrix field. Clearly, that's outside of what we've discussed so far. And similarly, if you take the Laplacian of a vector field, then we apply the Laplacian component-wise. Again, Navier-Stokes equations are not an adventure that we undertake in this class. It's more of a motivation, so you can see that with vector calculus you can also approach very complicated phenomena in physics and engineering. Let me just remark at this point, with our knowledge and our intuition on the divergence, we can already tell that in this formulation of the Navier-Stokes equations, or in this variant of the Navier-Stokes equations, the vector field u, being divergence-free, apparently does not have any sources or sinks. Finally, let's go from fluids to solids. Another partial differential equation that describes some phenomena in physics that can be stated again once more in terms of vector calculus is the so-called elasticity equation. The elasticity equations, of course, are particularly important in mechanical engineering. Here again we have got an unknown variable u, which is a vector field, and that vector field describes the deformation in space. If you have got a solid that is subject to an external force, for example gravitation, then the elasticity equations will describe how the solid deforms. The elasticity equations read as follows. Negative Laplacian of u, where u is the vector field, the deformation vector field, minus lambda plus mu, where these are the Lamé coefficients, those are just some material parameters that get involved in their elasticity equations. They describe basically the response of the material to external forces. That's multiplied with the gradient of the divergence of the vector field u. That equals the external force F. Let's finish that example with a picture. Let's suppose I've got a brick. That brick can be wood, can be concrete, can be some very elastic material. If I subject it to an external force, let's say, for example, this is a piece of a bridge and it is subject to gravitation. Then it will deform according to the gravitational field. In this case, the gravitational field has only one direction. It's very simple. And the deformation will describe how we move one point to the deformed position, so to speak. And the deformation vector field describes how this piece of material deforms when subject to the external force F. So if that is the rest position, I've got some point here, then the deformation vector field u at this point will point downwards. Similarly, for example, at this point, the deformation will get me to this point. These partial differential equations, and the one we have discussed before, are of tremendous importance throughout physics and engineering, in fact throughout all of mathematics. They have inspired research that has been going on now for centuries, and we are nowhere close to stopping and having finalized the theory of these equations. There's always more stuff to do. That being said, before we get even close to discussing such partial differential equations, we need to master the basic tools of vector calculus. And that will include, in particular, the basic integration theorems of vector calculus involving line integrals and surface integrals.